to have Gouvea here from Northwestern. He got his PhD at Berkeley in 1999, was a research fellow at CERN and Fermilab before moving to Northwestern, where he's now a professor. He's a fellow of the American Physical Society. And in my particle physics universe, people are interested in physics beyond the standard model, and one of the most interesting avenues to look at physics beyond the standard model is in the form of neutrino mass, which is one of the things that's unexplained. And Professor Gouvea is one of the world's foremost thinkers about this in a wide variety of different avenues, and today he's going to give us his take on this brave new world.
Okay, so thanks a lot for having me. So my job is to tell you a little bit about the physics that's been going on with neutrinos. And I will start at the very beginning just to give you a flavor of what neutrinos are, and then I'll move on to hopefully give you a sense of what it is that theorists think about when they ask about neutrinos. The title of the talk is just meant to be funny or cute, so hopefully that worked. And I will have nothing to say about the book, The Brave New World, other than if you've never read it, you should read it. And you should definitely read it now. And I think the thing that's most scary about the book is that it's not scary anymore. So I want to talk about particle physics. So for people who are not in particle physics, this is a chart of all of the fundamental particles that we know about. If you've never seen them in this form, this is what they really look like. We don't like to talk about that very much. And of course, you know about the particles in particle physics. You have your fermions that sit on this side, and then you have your bosons that sit on this side. We've all heard about quarks and leptons. The particles that I do want to talk about are the neutrinos. So the neutrinos are fundamental particles, and they are among this select few that we've identified as the fundamental building blocks of nature. So these are the particles that I want to talk about, and I also like that picture as well. So neutrinos are special particles. As far as we know, they don't decay. So every time you produce one, unless it gets detected, it will stick around. And it turns out that neutrinos are very, 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 very abundant. So these are particles that are produced in very large numbers in the sun. This is something that hopefully you've heard about before. If you never have, it's a nice, useful number to have. The flux of neutrinos from the sun is more than 10 billions per centimeter square per second. So we are bombarded constantly by neutrinos from the sun all the time. And this is hopefully something that people have heard about and hopefully that they appreciate. I have no idea why that happened. Neutrinos are also produced in nuclear reactors. This is so weird. This never happens to me. So let me do that. This was working perfectly before, so let's do that. Let's go back to this. So like I try to say very quickly, neutrinos are also produced in radioactive processes everywhere. In particular, if you have a nuclear reactor, that's a place where you collect a lot of radioactive decaying material in one place. So that's a great place to look for neutrinos. And of course, neutrinos are also heavily produced by collisions of cosmic rays with our atmosphere. So they're actually produced in lots and lots of different places in very large quantities. And these are the sources that we use in order to study neutrinos. I want to point out just a couple of other random things that are very important. Neutrinos are also produced in other astrophysical objects as well. So for example, neutrinos are known to be produced in supernova explosions. There was one supernova explosion that happened not too long ago in 1987. And we actually got to see neutrinos coming from there. So this is a picture of the supernova explosion and then the remnant on the right-hand side. I think that's what it is. I always forget if it was this way or that way. But the one thing that I always like to point out, and I won't be talking about supernova neutrinos at all, but just something to keep in mind, supernova explosions are very impressive. That's why they get these names. Super is sort of something that's supposed to be very, very impressive. And they stick out, as everybody knows. Supernova remnants, the light of a supernova was observed for days and days in Kepler's time, for example, and that was sort of a big deal. So they're very big, bright events that you can see. And the thing that's most important to keep in mind is when you see a supernova explosion, which we haven't seen for a very long time, these very bright objects, you should keep in mind that the light is a very tiny sideshow of what's actually going on in a supernova explosion. The best way to picture what a supernova explosion is that you're taking a certain amount of mass and you're basically converting that into neutrinos. The light is a side effect. It's like less than 1% of the energy that comes out has anything to do with light. Most of the energy that comes out, more than 99%, comes out in the form of neutrinos. So if we could see these supernova explosions with neutrino eyes, we would see a much more impressive event. And of course, the other thing that I want to point out is that neutrinos are also relics from the Big Bang, we think. So we think we understand more or less the history of the universe, at least as we go back. And we have a lot of indirect evidence that these neutrinos are there. They are these relics of the Big Bang. And their numbers are gigantic. So neutrinos are as abundant as photons from the Big Bang. So this is sort of a plot of that. This is to give you a feel of how many particles per cubic centimeter there are. This is how many photons and neutrinos there are. This is how many protons there are. Protons and electrons happen to be the same because the charge is 0 for the whole universe. Then there's some neutrons, which is about the same as the protons in this scale. Then there's this thing called the dark matter. We have no idea how much dark matter there is. If you take your favorite generic model, this is probably as much dark matter that there is. So the number of neutrinos that was produced in the early universe is also gigantic, and we have no evidence to believe that they haven't that they have disappeared, so they're still around. So neutrinos are produced today, they're produced in the past, they're produced in the planet and in the sun and so on. And the reason they're not subject of everyday conversation is that even though we can produce tons of them, they are ridiculously hard to study. And again, this is aimed at people who don't think about this on a daily basis. Even though there's so many neutrinos, they are really hard to detect. There are lots of analogies that people like to give. Here's one of them. If you wanted to build a detector that has 50% probability of absorbing a neutrino from the sun, and you make your detector out of lead, which is a nice dense object, that detector has to be about the size of the solar system, more or less, up to an order of magnitude. So neutrinos are very, very, very hard to detect. And the reason for this is very well understood. They only interact via the weak force. And all of the circumstances under which we detect neutrinos are such that the weak force is deserving of its name. It's really, really weak. So the probability of a neutrino hitting something is very, very small. So how do we get around this? How do we get to study neutrinos at all? One component of this is that there are lots of them. So they are, in some sense, very easy to produce in abundance. And the other component of this, which is very important, is that people figured out how to build very, very big detectors that allow you to make precision measurements. So this is the challenge of neutrino detection has always been, how do I build a detector that's big enough and massive enough that I can get enough of these neutrinos hitting my material on the one hand, but on the other hand, how do I get to detect anything? Because if I have a very dense material that's being hit by these neutrinos, the byproducts of the collision, which is the stuff that I measure, will also be eaten up by this material that I've used to build my detector. So that's the experimental challenge, and people have gotten very good at doing this. I don't want to talk about the experiments. People can ask me about that as much as they want. But I want to give you a sense of how our understanding of neutrinos has changed from a fundamental physics point of view, and what types of questions we're asking of neutrinos today. So here's a one-slide summary of what happens if you take a particle physics book that wasn't written last year, and you ask, what does the particle physics book have to say about neutrinos? So neutrinos are produced in flavors, and they come in 3 flavors. The flavors are the electron neutrino, the muon neutrino, and the tau neutrino. This name comes from the fact that when you have what's called a charge current weak interaction, the neutrino is produced together with a charged lepton. And there are 3 charged leptons, the electron, the muon, and the tau. So the neutrino that's produced together with the electron is called the electron neutrino. This one is called the muon neutrino. And this one here is called the tau neutrino. Now, these neutrinos are all different. We've done experiments to convince ourselves that if you measure this electron neutrino later on, it can only produce electrons when it hits something. The muon neutrino can produce muons when it hits something, and the tau neutrino can produce taus when it hits something. So it's in that sense, and again, I'm saying this as a matter-of-fact statement. It took our community a couple of decades to figure all of this out. Lots of fun experiments and a lot of confusion led to this picture. Neutrino interacts only via the weak interactions, so I've already said that. Until a decade or a couple of decades ago, we believed that neutrinos didn't have any mass. And that's a lot of what I'll talk about has to do with neutrino masses. So let me just tell you a few interesting things about particles that are fermions and don't have any mass. The most interesting thing about particles that are fermions and don't have any mass is that they still have spin. But if they don't have any mass, you can label the particle by its helicity. So the particle is either, say, left-handed or right-handed. And what's interesting is if the particle doesn't have any mass, that quantum number is a Lorentz invariant. That means if you have a left-handed neutrino and it looks left-handed in the laboratory frame, it looks left-handed in any frame. And if you had one that was right-handed, it would look right-handed in any frame. So you can label them by their handedness in a very, very unambiguous way, as long as they're not massive. So taking this into account, because the neutrinos interact only via the weak interactions, it turns out that all of the neutrinos that we produce are left-handed in the laboratory. We have no evidence of being able to produce a right-handed helicity neutrino. All of the antineutrinos, on the other hand, are right-handed. This means from a field theory point of view, if you want to describe the neutrino with a quantum field theoretical object, that object has only 2 degrees of freedom. That means that the only degrees of freedom that I need are the left-handed neutrino and the right-handed antineutrino. Those two, by the way, are connected by the CPT theorem. So we know that if a left-handed neutrino exists, the right-handed antineutrino has to exist as well. So neutrinos were very economical until this century, that they only needed 2 degrees of freedom in order to be described. There's another thing that I want to mention very briefly is that neutrinos carry another quantum number that's not apparent here, but it's called a lepton number, which means that neutrinos, when they hit something, they always produce charged leptons with negative charge. So a neutrino will produce an electron or a muon or a tau, depending on the flavor, and the antineutrino produces the positron or the antimuon or the anti-tau. Now, something very interesting happened that changed and told us that this picture was wrong. So again, this is a picture that I told you about, and actually I lied. That picture is not correct. And what we've learned is it is possible to produce what we think is either a muon neutrino or an electron neutrino, let it propagate a certain distance, and when we measure it, it actually can behave as a different flavor. So it's possible to produce a muon neutrino and detect it as a tau neutrino. It's possible to produce an electron neutrino and detect it as a muon neutrino. And the evidence for this phenomenon, which we call neutrino flavor change, is absolutely overwhelming. We've done experiments with different neutrino sources. We've done experiments with different neutrino energies. We've done experiments with different baselines for the neutrinos. And we're very, very, very sure that this happens. So there's no doubt that this happens. It's a fact. And the other thing is that this phenomenon depends on how long the neutrino propagates. So it's kind of funny that when we were constructing, say, this model here, and when we convinced ourselves that the muon neutrino was different from the electron neutrino, we kind of got lucky because we only did experiments with a very, very short baseline that this phenomenon didn't have enough time to manifest itself. If somehow life had been different, we would have gotten even more confused, which would have been fun, but it didn't happen. But what happened is you have to wait a long enough time, or the neutrino has to propagate a long enough distance in order for this phenomenon to turn on. So by taking all of these data into account, and by appreciating the fact that this phenomenon depends on the energy and the baseline, we figured out that the only explanation for all of these phenomena is to postulate that the neutrinos have mass, and to assume that the leptons can mix just like the charged fermions, just like the quarks. Charged fermions would be a different story. Let me explain the physics responsible for that because it's easy to understand and it's kind of cool. I will give you the back of the envelope explanation of this phenomenon, but people get confused and they are entitled to be confused, and I'm happy to say more about that later if people have questions. But it's easy to see. What happens is, imagine that you postulate now that the neutrinos have mass. So that means that instead of calling the neutrinos via how they interact via the charge current interactions, I can label them by their mass. So I can say, you know, neutrino number 1 has mass m1, neutrino number 2 has mass m2, and neutrino number 3 has mass m3. So that means that there are two different ways of labeling my neutrino. So you can ask yourself, how are these neutrino mass eigenstates, that's what we call them, are related to these so-called neutrino interaction eigenstates or neutrino flavor eigenstates? And the picture that we use is to say that clearly they don't have to be related in a one-to-one case. You know, it doesn't have to be that the electron neutrino is the same as a neutrino with mass m1. But the most general statement you can make is that the electron neutrino is some quantum mechanical linear combination of these neutrinos with a well-defined mass. And the muon neutrino is another linear combination of these neutrinos with a well-defined mass. And the tau neutrino is yet another linear combination of those neutrinos with a well-defined mass. Now, because the electron, the muon, and the tau neutrinos are different objects, I can classify them as different, and the probability that one is the other is 0. These coefficients of these linear combinations define a unitary matrix. Okay, and we'll come back to this in just a second. So what has that got to do with the neutrinos changing flavor? The idea is very simple. Whenever we produce a neutrino, what we can produce via the charge current weak interactions are these things here, these eigenstates of flavor. Okay? On the other hand, you can ask, you know, what are neutrinos with a well-defined mass? Neutrinos with a well-defined mass are eigenstates of the propagation Hamiltonian. So they are eigenstates of the Hamiltonian of a free neutrino. So that means if I produce a neutrino and I ask what's the time evolution of that, the thing which is an eigenstate of that Hamiltonian is the neutrino with a well-defined mass. So again, you know, if I produce a neutrino with a well-defined mass, somewhere else after some amount of time, that neutrino will stay an eigenstate of a well-defined mass, and it picks up a propagation phase factor. And this phase factor is characterized, you know, if this is a non-shell particle, this particle has some energy and some momentum, and it obeys the usual dispersion relation. So this is just a plane wave. So neutrinos with a well-defined mass propagate as plane waves. So if I produce an electron neutrino, and if I lived in a world with only 2 neutrinos because it's easier to explain that way, then the electron neutrino would be a linear combination of the neutrinos with a well-defined mass, and the muon neutrino would be a linear combination of neutrinos with a well-defined mass. So if I ask how does this state here propagate as a function of time, the electron neutrino is not an eigenstate of the Hamiltonian, but it is a linear combination of those eigenstates of the Hamiltonian. So the way that we solve this is that this eigenstate component picks up a phase, and this eigenstate component here also picks up a phase. And the end result, of course, is that as a function of the time that the neutrino propagates, this object that I'm left with is no longer the electron neutrino, it's some other object, because it's not an eigenstate of the Hamiltonian. Now, this is very, very simple physics that everybody has seen before. I see that there are a lot of people here who are more grown up than undergraduates are. But if you've ever taught quantum mechanics, this is hopefully the very first quantum mechanical system you talked about. Maybe not with momenta, but this is like a 2-level system in quantum mechanics, where you start out with a linear superposition of the 2 eigenstates of the Hamiltonian, and then you ask how does that state evolve. The physics is exactly the same. So you can then ask what's the probability that this thing that was born as an electron neutrino is detected, for example, as a muon neutrino, and that of course is just this matrix element squared. Now we do some kinematics because we want to say the neutrino is produced here at some point in time, and it's detected there at a different point in time. We make some approximations, including the fact that neutrinos move very fast. And if we plug this in, we can calculate this probability here, and we get something that should be very familiar to people who've taught quantum mechanics before. this probability that you start out as some state and you end up as the other state has some amplitude which is proportional to the linear combinations that you started out with. And then there's some sinusoidal function that's proportional to the difference between the two energy levels. And in this system, that difference between the two energy levels looks like the difference of the masses squared, because the difference in this phase comes from the fact that the two mass eigenstates have different dispersion relations, and it's proportional to L over E, which is my time in a relativistic system. Okay, so this is a very familiar result. And the point then is that if I do an experiment, I can produce an electron neutrino and measure it as a muon neutrino as a function of what we call the baseline L. And the form of that looks like a sinusoidal function. And the parameters of this function that we care about are the amplitude and the frequency of the oscillation. And the amplitude is some nature's parameter, which is how much is this mixing between, how much of the electron neutrino is neutrino number 1 and neutrino number 2. And the frequency of the oscillation is proportional to the difference of the neutrino masses squared. Okay? So that means that by postulating that neutrinos have mass, I can get this flavor changing phenomenon. And then I can take this and I look at my data and I can ask, does this hypothesis fit my data? And for what values of my neutrino masses and mixing angles do I get a good fit? Let me just say very briefly something about the fact that there are 3 neutrinos and not 2. You can tell the whole story again with 3 neutrinos. The only thing that changes is that now the mapping between the flavor eigenstates and the mass eigenstates is some 3×3 unitary matrix that we call it, it has lots of names. I'll call it the leptonic mixing matrix. And this mixing matrix here, of course, is parametrized by a certain number of free parameters. And for our purposes of this talk, the number of free parameters is 4. And those 4 parameters can be thought of as 3 mixing angles. So there are 3 trigonometric angles that I can write like theta 1, 2, theta 2, 3, and theta 1, 3. And then there's a complex parameter as well. So this is a unitary matrix. That means the entries are complex. And if I get rid of all of the redundancies in parametrizing this matrix, I'm left over with another number here that is a complex number. Okay, so it's the phase of a complex number. There's another funny technicality, which is I told you that neutrino number 1 has mass 1, neutrino number 2 has mass m2, and neutrino number 3 has mass m3, but that doesn't define what these states are. So in order to unambiguously define what these states are, I have to tell you what the masses are. The problem is I don't know what the masses are, but I still have to tell you what these states are. So the way that we do that is very confusing. So I will try to say this in words, and I'll show you a picture in just a second. The way that we choose to do this is by telling you how these masses are ordered. So instead of telling you that neutrino number 1 has mass 1 electron volt, I tell you that neutrino number 1 is lighter than neutrino number 2. So if I only had those 2 neutrinos, that would be an unambiguous definition of what those neutrinos are. There's a third one. So the question is, how does neutrino number 3 fit within this 1-2 pair that I've just defined which one is heavier? And it turns out that we choose a funny definition. The definition is that neutrino number 3 is either much heavier than the other 2 or much lighter than the other 2. In such a way that this difference here is always bigger than this difference here. Okay? That's a definition of how we do things. We didn't have to do it that way. We could have done something different, like neutrino number 1 is the lightest one, neutrino number 2 is the second lightest one, and neutrino number 3 is the heaviest one. But we chose not to do that because we wanted to confuse people. Actually, we chose to do that because if we didn't do that, there would be some ambiguity in mapping experiments into the elements of this matrix here, and we definitely didn't want to do that. So that would have been worse. So this is the best we can do. There's another way of doing this, but I don't want to talk about it. So it turns out then that because of this choice, this difference of masses squared, which is the thing that my experiments care about, this one here, m2 squared minus m1 squared, is positive definite. This one here, m3 squared minus m1 squared, is not positive definite. It's either positive or negative. And that sign, plus or minus, isn't observable. So, we've done a lot of work since we've discovered that neutrinos oscillate. We can take this simple idea and we can ask, can we explain all the data? The answer is yes. These are all of these parameters that we have. This is a very long, complicated table that we don't want to look at. But I do want to mention some things which are very important. One is, in my professional lifetime, this is the one part of our understanding of nature that changed the most by a lot. When I started grad school, we didn't know if any of those numbers existed. We didn't know if anything was physical there or not, because the masses were supposed to be zero, and then everything that I'm talking about is totally irrelevant. So we went from not knowing if any of this exists to actually measuring all of these parameters and actually measuring some of them really well. So some of these measurements are at the 5% level. So again, it's a new phenomenon that was discovered about 20 years ago, and we've been able to explain the phenomenon, and we've been able to constrain the physics that's responsible for this phenomenon at the 5 to 10% level. So this is a very, very impressive achievement that happened very quickly, especially in neutrino time units. The neutrino is a particle that was very hard to study. So I'll just give you the quick history. The neutrino first manifested itself probably in the 1900s when people measured beta decay and they thought energy and momentum were not conserved. Then the neutrino was invented in 1930 to explain why energy and momentum are conserved. And then the neutrino was first detected. So it was from a hypothetical, theoretical particle. It became a real particle when it was first detected in 1954. So that is 25 years after it was invented, it was first detected. And then the second neutrino was detected a decade and a half later. And the last neutrino was detected in 2001. So life is hard in the neutrino world. But this happened very quickly. The other thing I want to mention is that we do have information on the neutrino masses, at least on the differences of the masses squared. But the important thing is that the masses are very small. So this is a particle physics talk, so we measure masses in electron volts. And I'll show you a plot in just a second. The electron mass is 511 kilo electron volts. And if you're a particle physicist, that's a really small mass. The neutrino masses are known to be less than 1 electron volt, and maybe less than 0.1 electron volts. So I'll come back to this. This is the other big surprise. I do want to show one data plot. This is the last mixing angle that we measured. This is a beautiful result because it shows that we think we understand what's going on. This is a result from a reactor neutrino experiment. We produce neutrinos in a nuclear reactor. We detect them nearby. Then we detect them far away. If they're oscillating, we can calculate the probability that these neutrinos will be disappearing as a function of time. That's the functional form that we have. This is the fit to these data. If you're not impressed because you work with experiments that have lots of data points, I can't do anything about that. But this is a really impressive fit. And the thing that makes this fit very impressive is the fact that when they were performing this fit, they already knew what the oscillation frequency was supposed to be, because we had measured that from another experiment. So this is a one-parameter fit. The only thing we didn't know was this mixing angle, and it didn't have to work, but it worked really well. The other thing I want to say is that this experiment was made possible because of our understanding of the neutrino oscillations. So we chose everything about this experiment because we already knew enough about neutrinos in order to predict that something has to happen if you do this very particular experiment here. So that means we're in the business of asking questions and understanding with a large degree of certainty that we know what experiment we have to do next in order to get an answer. So this is a picture of where we stand. So you can ask yourself whether we've learned enough and we should go ahead and do something else now. And the answer is no, because that's what I'm contractually obliged to say right now. So if you ask about neutrino oscillations, this is a picture of the neutrino masses, by the way. This is 1, 2, 3. This is one way in which they could be ordered. The other one is this 3, 1, 2, and this is the other way in which they can be ordered. And it turns out, with all the data that we have today, we don't know if the picture looks like this or like that. That's one thing we haven't figured out yet. I do want to point out that that's because of the nature of the observables that we have. But it is important to keep in mind that this picture is really different from that one. Okay? And you know they are because they look different. Look, it's different. Okay? So the physics, the answer is important and it tells us something we don't know. The other thing that's depicted here are these mixing angles. One way of interpreting the mixing angle is that if you have a neutrino number 1 and you make a measurement on that, you can ask what's the probability that that's an electron neutrino, or that behaves like an electron neutrino, and that's proportional to one of the mixing angles squared. So the fraction of these bars that are colored a certain color is the entries of the mixing matrix squared. So for example, if you look at neutrino number 1, it has a large probability of being an electron neutrino, a medium-sized probability of being a muon or a tau neutrino. If you look at neutrino number 3, it's mostly made out of muon and tau with a small contamination of electron neutrinos.
Are those the same on the left and the right? They look close, but it's not clear.
What the same?
Well, if you look at...
You mean the sizes of the bars?
No, if you look at M1 squared on the left and M1 squared on the right, the proportion, well, it looks like...
They're supposed to be the same.
They are the same. Okay.
But it is a cartoon. The cartoon is not incorrect, okay. But it should give you the right picture, let's say.
But the proportions are the same.
That's correct, absolutely, yeah. And so like I said, we don't know the ordering. And then the reason I'm talking about these pictures is that there's another question that people like to ask. The other question that people like to ask, if I stare at all of these bars that I wrote down here, you notice that the blue and green are always in the same amounts. Okay, so for example, if you look over here, green and blue, same fraction. Here, green and blue, kind of same fraction. Here, green and blue, the same fraction. So we don't know, for example, if you look at neutrino number 3, if it's more green than blue or the other way around. We don't know the answer to that because our data are not precise enough. So that's another question you can ask. Another thing which is not drawn here is this CP odd parameter, or this complex parameter that I told you about. That's really hard to draw, so we're not going to draw that. We only draw the magnitude squares of things, although they do have an impact in something. And that's something we also don't know. And this turns out to be important, and I'll talk about that in a little bit more detail, but it's related to whether CP invariance is violated in neutrino oscillations or not, whether neutrinos and antineutrinos oscillate in the same way. So this is another important question. So this is sort of the list of questions that we can ask. And all of these questions here can only be answered by neutrino oscillation experiments. We don't know how to answer all these questions in any other way. That's not totally true, but let's pretend it's true, just for the sake of the argument. So this is what we're after. And one thing which I also like to say is when people talk about doing the next really big neutrino oscillation experiment, and they say this is what we're trying to measure, it is often the case, or people come out with the impression that that sounds like a lot of work for very little gain. We're just measuring a bunch of numbers that we don't know, and what are we going to know at the end of the day? I think a better way of asking the question is to say that we have built this really nice picture that explains all the data. But do we actually have the right picture? So are we sure that this is really what's going on and not something else? Or is there some other ingredient to this that we're missing? So our job is not just to measure all of these parameters, but in some sense we like to measure them really well and in lots of different ways. Because what we're really after is not measuring a bunch of numbers, we're after testing the formalism. We want to know if these ideas are correct or not, or if we're missing something. I really like this picture. If you're in particle physics, you know about mixing because of the quark sector. And in the quark sector, we have the same sort of objects as well. We have these mixing angles, and we can measure all of them. And this is a measurement of some combination of those mixing angles. So if you've never seen this before, every colored line here is a different measurement. Okay, so if you measure, if you do some experiment, you get the answer is these blue lines. Another experiment is this green circle. Another experiment is a yellow circle. So you're measuring the same thing in like 30 different ways. What's really impressive is the fact that if your theory is correct, all of these different measurements have to meet at a point. If your theory is wrong, they won't meet at a point. Now, I am sad to report that all these measurements meet at a point. They meet right here, which is sort of disappointing, but that means that we've tested this idea very well. So you can ask yourself, have we done that in the neutrino sector? And the answer is not at all, not by a long shot. Okay? And just to give you a sense, this is my mixing matrix. And remember, I said that we can measure the parameters of this mixing matrix at the 10% level or even the 5% level. But when we do that, we're kind of cheating. When we do that, we assume, for example, that this is a unitary matrix. And then we use that to constrain all of my parameters. If you ask yourself what we've actually measured directly, we've measured this number here really well, the magnitude squared. We've measured this number here, magnitude squared, very well. We've measured the products of the magnitudes of those two numbers very well. We measured this number here squared very well. And then we measured this number here very crappily, very poorly. That's what we've measured. That's it. So we are still a very, very long way of figuring out or even testing whether this can be a unitary matrix or not. People have done studies of this. There's some unitarity tests you can try to perform, and they are done at, I don't know, a 10% level or 50% level. So we're very far away from testing this. So that's message number one. I do want to say some things about CP violation. And let me very quickly tell you what the CP violation observable is. So one thing you can ask is, I can do a neutrino experiment, and I can measure nu mu to nu e oscillations. And then I can compare that with nu mu bar to nu e bar oscillations. So one is whatever the particles are doing. The other one is whatever the antiparticles are doing. And then I can ask if these oscillation probabilities are the same or not. If they're not the same, then matter and antimatter are doing something different. And we call that CP violation. Okay, it's a longer story, but I don't want to get into it. So we can calculate the amplitude. So this object here, absolute value squared, will give me this probability. And this object here, absolute value squared, will give me that probability. This is very similar to what I wrote down before, but in a more sophisticated way. This is the mixing angle part, and this is the e to the I et part, which I wrote in some convenient way to make life look easier. But we don't need to care about this. We can stare at this complex number here, and we can stare at this complex number here, and first we note that they're not the same because the couplings for particles and antiparticles are flipped. So this mixing angle part here is a UE star U mu, and this is UE U mu star. So these things are not the same. So the question you want to ask yourself is, if I look at this complex number here squared, is it possible that it's not the same as this complex number here squared? And if the answer is yes, then I can look for CP violation in neutrino oscillations. If the answer is no, then I can't even do the experiment. And this is the exercise that we have to go through in order to figure out what experiment we need to do. And the one thing I want to point out is, if you look at this, both of these amplitudes are a sum of two terms. Okay? And you should be able to convince yourself that if any one of those two terms is 0, then this number squared is the same as that number squared, even though the complex numbers are different. So I need both contributions to the amplitude to be there. So that means that I need all the entries of my mixing matrix to be non-zero. If any entry is 0, this object here does not violate CP. The other less trivial thing that I need is, if you look at this term here in parentheses, it looks like e to the I something minus 1. So if that something is really small, e to the I something very small is 1. So that means that one of those two terms will vanish. You can't do the experiment either. So in order for you to be able to do this experiment, you have to make sure that these phases here are big, or big enough. And this phase is proportional to the size of your experiment, your distance for the experiment. And that gives you a feel for how long you need your neutrinos to go so you can measure this. So this is just a summary of all of that. And that tells us that we know how to engineer this. And this is a picture of what this could look like. For example, I could do an experiment that looks for nu mu to nu e, or nu mu bar to nu e bar as a function of L over E. And I would say that, for example, maybe the neutrinos are doing this, and maybe the antineutrinos are doing that. And then I would be very happy and say that CP is violated. Of course, when you do the experiment, you never get to see this. You normally do an experiment like here, if you're lucky. Okay, so that's the kind of experiments that you do. If you're very lucky, maybe you can come all the way out here. So that's what you're trying to measure, and that's what makes this challenging, but at least it's possible. So I want to give you a picture of how much we already know about CP violation. That's characterized by this delta CP parameter. That tells you whether neutrinos and antineutrinos can oscillate differently or not. If that number is 0 or 180 degrees, then neutrinos and antineutrinos oscillate in the same way. And with all the data that we have access to, let's only look at the top panel here. The difference between the top and the bottom is how the neutrinos are ordered. So if the neutrinos are ordered this way, you extract your parameters and you get certain numbers. If they're ordered this way, you extract your parameters and you get almost the same numbers, but not exactly the same. So you have some sensitivity to the ordering. So if you look here, you notice that 0 is almost ruled out, and 180 degrees is not ruled out, at least for this ordering. If the ordering is inverted, you would be tempted to believe that life is better, but not really. The reason it's not really better is because of the fact that the best fit point for this analysis is here. So these points are already a little bit ruled out to begin with. So anyway, we don't want to get into those details. But this is probably a better sense of the picture. So we're getting to a point where we might be able to say something about CP violation, but the goal is to wait for the next round of experiments. This is another fun plot. Again, we want to concentrate on this right-hand side here. This is the equivalent of this plot that people do in the quark sector. Okay? And what we're plotting is this region over here in the neutrino sector. What do we know about that? And this region over here looks like that. So it's a little bit bigger. And on top of that, when we make this plot, we're actually cheating because we assume the matrix is unitary. So if we don't assume the matrix is unitary, this region is way bigger because we don't have that many observables yet. But it is a step in the direction of actually trying to measure this. I do want to say something about the importance of making this measurement, but I'll use a particle physics language for that. So basically, one thing that we care about a lot, which has a lot of important implications, is does matter and antimatter behave differently? And can you tell that something is matter? What's the distinction between those two things? The masses are the same, the charges are related, and so on. And it turns out that in the standard model of particle physics, there are 5 different ways in which matter and antimatter could have behaved differently. That means that there are 5 degrees of freedom in the formalism in principle that tell you that matter and antimatter could have behaved differently. 5. So 5 free parameters. Those we have to measure, of course. One of those parameters is a CP odd phase in the quark mixing matrix, just like the one that I was talking about before. We've actually measured that one. It's a large number. It's like 70 degrees. It's an angle, so you measure that in degrees. There's another number which lives in the QCD sector. It's called the theta QCD parameter. That number is also a phase. It's any number between 0 and 360 degrees. We've never measured it, but we know it's less than 10 to minus 10. Okay, so these are 2 CP violating parameters. One is 70 degrees. The other one is less than 10 to minus 10. All the other parameters live in the neutrino sector. None of them are physical if neutrino masses are 0. So those other 3 parameters all live here. And one of those is the one that we can measure with neutrino oscillations. So it's important to appreciate the fact that, first of all, most of the CP violation in the standard model is in the neutrino sector. Everything else is only 2 parameters. So that's one important point to keep in mind. The other one which is important is if you were to ask yourself, what do you think that number will be? You have to remember that we have only two other parameters. One is 70 degrees, the other one is less than 10 and minus 10. So learning what these other numbers here are is probably important because we don't have a lot of guidance right now. To be fair, this number that's less than 10 to the minus 10, we think that happens for a reason. A very special reason that might be very important for things like dark matter and so on, but we have no idea if that explanation is correct or not. It sounds correct, it works really well, but we have no evidence that it's true because we don't have any experiments that tell us that this is correct. So learning about CP violation in the neutrino sector, I think, is much more than a repeat of what we've done in the quark sector. It's actually new information that we don't have. And I will say that speculating is very dangerous. One thing that I always like to point out is when we started postulating that maybe neutrinos mixed, everybody's gut reaction was to say that, yeah, they probably do if they have some mass. And the mixing is probably like what happens in the quark sector. In the quark sector, the mixing angles are really small. So people postulated that, of course, neutrino mixing angles are very small. And that's half of the reason why people didn't believe in neutrino experiments to begin with. Because they were saying something weird. Why are these mixing so large? Clearly, these experimentalists did something wrong. Or, if we found a solution where the mixing angle was very small, we said this must be the answer for what's happening with the solar neutrinos. And all of those prejudices turned out to be prejudices. And they also turned out to be completely wrong. Not just a little bit wrong. They were really wrong. They were completely wrong. So guessing what happens in the lepton sector based on what you've learned in the quark sector is a dangerous thing to be involved in. So where are we in terms of experiments? In terms of experiments, we have a lot of experiments going on today, and lots of experiments in the future that are aimed at testing whether our understanding of the neutrino sector is correct, and at the same time looking for CP violation in the neutrino sector, and perhaps telling us about a new phenomena as well. So there's a large program that's in place, including a very large experiment that's being proposed here in the United States, that would start taking data, I would say, less than a decade from now. And a lot of work has to be done in order to develop new kinds of experiments that are very big, and new kinds of neutrino beams that are very intense, in order for us to ask these very sophisticated questions about our neutrinos. So let me tell you what are the other things we don't know about neutrinos that are interesting to ask. Another one is I've told you that we can measure the differences of the neutrino masses squared. That's what the oscillation experiments can measure. But you're allowed to ask, what's the neutrino mass proper? Not just the differences of the masses squared. And the answer is we don't know. And we can't learn that with neutrino oscillation experiments. And this is an important question. It's not just another number, but it changes the way the scenario looks. So one way of parameterizing this is, if we knew any of the masses, we could figure out all the other ones because we know all the differences. So we can say, let's postulate, let's parameterize our ignorance by the lightest mass. So what's the lightest neutrino mass? And there are lots of different answers. Maybe the lightest mass is exactly 0, or very, very close to 0. That would probably mean something interesting. Or maybe the lightest mass squared is way bigger than the differences of all the masses squared. That would indicate that the masses are almost exactly the same. That would be very weird if that turned out to be the case. Or maybe it's somewhere in the middle. And there are lots of different kinds of experiments that are sensitive to this. I want to just mention the fact that cosmology gives us some information about the neutrino masses. And the reason for this is easy to understand, hopefully. I said that in the early universe, a lot of neutrinos are produced. They have a strong impact on the expansion rate of the universe. That's why we have indirect evidence that they're there. And if you follow the thermal history of the universe, at some point, those neutrinos, and there are lots of them, they start to behave like a non-relativistic gas, as opposed to a relativistic gas. We expect that when that happens, that leaves some imprint in the universe. And in particular, it leaves an imprint in large-scale structure. So the formation of galaxies and clusters of galaxies knows about the fact that at some point, a part of your energy density went from relativistic to non-relativistic. That's the hand-wavy explanation of that. People analyze data asking, what does cosmic surveys tell you about neutrino masses? This is an old plot. This is supposed to be a probability distribution for the sum of the neutrino masses, just to say which values are more likely. the reason I like to show this picture is that there are lots of lines. And what changes here has to do with what do you say about all the other cosmological parameters, which kinds of data sets do you consider in your fits, and so on. So life is hard, but you notice that the probabilities get very small above some fraction of an electron volt. So we like to believe that the cosmological data constrain the neutrino masses to be below an electron volt. And that's a 2012 paper. Things have changed a little bit, especially after a new Planck data and so on. The situation now is probably more peaked this way, if you wanted to draw it that way. But it is important to keep in mind that when people make these measurements of the neutrino mass, the neutrinos don't do anything. They're not even touched. You know, they're doing nothing. You're measuring the large-scale structure of the universe. You assume that you understand the thermal history of the universe, and then you convert that into a neutrino mass measurement. So it's a very dangerous measurement, especially for people like me who don't know what's going on. So it is tricky, and it's very dependent on other things that go on into the thermal history of the universe. But it is a very powerful probe. And one thing which I like to mention is, again, we don't know the lightest neutrino mass. But on the other hand, once we know that, we know what the sum of the masses are supposed to be. And if you talk to your cosmology friends, they claim that they should be able to measure a non-zero sum of the neutrino masses by the next decade with very, very good error bars. Again, these bands here depend on whether the ordering of the neutrino masses is one way or the other. And this is representative of what they think their error bar should be. This is one error bar, this is another one. This is a log scale, so this error bar is about as big as that one. So it's very exciting that I think they should be able to be telling us that the neutrino masses are not zero just from cosmic surveys. And of course, what we're really looking forward to is to get an answer from them that doesn't agree. That means that we're missing something. And that's what we're hoping will happen. That's probably not what will happen, but you never know. So, but it's very exciting. And I think it's become a big thing in for these cosmic surveys that they discuss in great detail how well they can constrain the non-zero neutrino masses. Okay, so in the last 5 minutes, I want to try to explain the last thing we don't know about neutrinos, and then I'll stop. So what else don't we know about neutrinos? The last question we can ask has to do with what's called the nature of the neutrino. And the question is, are the neutrinos Dirac fermions or Majorana fermions? So I want to try to explain what that means in words. And I will probably fail, but just bear with me. So the idea is very simple. We're all very familiar with the electron. So the electron is a Dirac fermion. We all know about that. So let's construct the electron very slowly. So let's say you do an experiment, and you discover there's a particle that has negative charge, and it's left-handed in your experiment. You can use the CPT theorem to tell you that there's another particle that you must also discover, which is a right-handed particle with positive charge. We know that those particles have to exist because of the CPT theorem. If you do more experiments with your electron particle, you figure out that the electron has mass. So if you ever see a massive electron that's left-handed, you know for a fact that there's another degree of freedom that we call the right-handed electron. That's a very simple statement, but it is an important one. It's kind of like saying you do an experiment with an electron at rest, and you figure out that the electron has spin up. So the statement I'm making is that that electron, there's another degree of freedom that's independent from the spin up, which is a spin down. That exists. And if you don't believe me, you just sort of turn upside down and you see the electron with a spin down, and there it is. And these are two different states. That's the important part. And of course, if the electron with a spin down exists, or the right-handed electron exists, the CPT partner of that is a positron that's left-handed. So that's a Dirac fermion. It has 4 degrees of freedom. Now let's tell the same story with the neutrinos. So we know that left-handed neutrinos exist. There they are. So the CPT theorem tells me that right-handed antineutrinos have to exist. So this degree of freedom implies this one. Now we know neutrinos have mass. That means that the left-handed neutrino also implies the existence of another right-handed degree of freedom. And let's say that that degree of freedom is a right-handed neutrino. So if the right-handed neutrino exists, then the left-handed antineutrino has to exist as well. And if this turns out to be correct, then this is identical to the story that I told you about the electron. Now, with the neutrino, you have a choice that you didn't have with the electron. This relationship here, which is a sort of by Lorentz invariance, those things are related. This relationship here tells you that a left-handed object exists, and it implies the existence of a right-handed object. This here says that a left-handed object exists, so it implies the existence of a right-handed object. But nothing tells you that this right-handed object has to be different from that one. In the case of the electron, you didn't have that choice because the right-handed positron and the right-handed electron are known to be different things. One has positive charge, the other one has negative charge. You would never get confused. They're the same object. In the case of neutrinos, those things here don't have any charge. So it is a logical possibility that the CPT partner of the neutrino is the same as the mass partner of the neutrino. If this is the case, the neutrinos only have 2 degrees of freedom, even if they have a non-zero mass, as opposed to the electron, which has 4. So the question that we're asking then is, a massive neutrino, does it require 4 degrees of freedom to describe or 2? That's the question. And that's the Majorana versus Dirac question. This is not a subtle question. 4 and 2 are very, very different numbers. So you can ask, how come we don't know the answer to that yet? And the answer is, if the neutrino mass had been 0, we wouldn't be allowed to ask that question. It's a non-question. It doesn't make any physical sense. So that means the question only makes sense if the neutrino mass is not 0. That means you can't get an answer if the neutrino mass were 0. That means that whatever observable you can construct that can tell you the answer to that question better not give you an answer if the neutrino mass is 0. Okay, so that's the answer. So the end result is that whatever that observable is, it has to vanish when the neutrino mass goes to 0. So in units that we care about for the experiment, everything that we measure, that observable will be proportional to the neutrino mass in units of the energy scale of the experiment that you make. But neutrino masses are really small. So that means that the types of observables that you're trying to measure are really, really small, and that's why we don't know the answer to this. Okay, so I have run out of time, so I'm going to skip a lot of stuff. This is by design, not by flaw. So I'll just read very quickly if you want. So this is all the theory stuff that I was going to talk about. That's a trick. So, okay. So let me just finish with this slide. That's probably the last thing I'm going to say. No, let's finish with the real final slide. So again, I try to give you a picture of what's going on in neutrino physics, especially all the stuff that we've learned and all the stuff that we haven't learned yet. What I didn't talk about is the theory of this, but I will tell you that there's a lot of different theoretical options, and there's a lot of fundamental questions that we ask. I do want to leave you with these 2 questions, which are the ones that theorists will talk about the most. And I'll just tell you that these are the questions. They're not more sophisticated than that. The most important question that theorists like to address is the fact that even though neutrino masses are not 0, they are very small. Okay, this is very important. So the electron is the lightest other fermion that we know about, and it is 511 keV, and the largest neutrino masses that we know about are like 0.1 electron volts. That's really small. So the neutrino is kind of an outlier in terms of the mass world. So we think that means something. We think that's nature's way of telling us something very important. But we don't know what that is yet. So we're working on that. The second thing that people like to pay a lot of attention to is the fact that I told you about quark mixing. And then I told you about I mentioned quark mixing, and I told you a lot about lepton mixing. And in terms of numbers, those numbers are very, very different. The quark mixing angles are very small. The lepton mixing angles are very big. We don't know what that means, but many people think that means something very important as well. And a lot of research goes into this. But we've just sort of begun figuring out what's going on, but we're not there yet. And we still have a lot of work to do. I do want to finish with one thing, just because somebody asked. So I sent this very nice figure there. And so the title of the work is A Brave New World, which I'm sure you remember, sort of a dystopian future kind of a society. So I don't want you to believe that that's what I meant by the title. But I do want to remind you where that Brave New World comes from in the book. So if you read the book and you have great memory, or if you're a big fan of Shakespeare, the title of the book comes from Shakespeare. And it comes from The Tempest. And it is in this a very, very nice phrase by Miranda, who's the person who grew up in the island. And this is what she says. And this is what I hope is going on in the world of neutrinos. And we'll find out more in the next several years as well. So thank you. Sorry for going over time.
We have time for questions here before retreating to our reception. Questions from the audience?
So in the super K detector experiments in Japan, they found that most of the muon neutrinos oscillate to tau neutrinos, but not electron neutrinos. So is there any explanation for that?
Any explanation for that?
Yeah.
So it's the same phenomenon that I was talking about. That's taken into account. And that's a very important ingredient for extracting all of these measurements. So, so we take the Super Kamiokande data, which is actually stronger evidence that the muon neutrinos are behaving like something else that's not the electron neutrino. And we interpret that as new mu's oscillating into new taus. And that plays a big role. And they actually, the bottom line is that about, on average, half of your muon neutrinos, by the time they get to Super Kamiokande, if they're coming from the other side of the Earth, they have converted into tau neutrinos. It's not a subtle effect. And we've confirmed that in these accelerator experiments, like the MINOS experiment at Fermilab, and the NOVA experiment also at Fermilab, and the T2K experiment in Japan. They've all confirmed that this is actually what's going on, that the muon neutrinos are converting, most of them, by the time they get to the detector, if you pick the distance just right, that they're turning into tau neutrinos. So that's that we can explain quite well. It's a big ingredient of the whole picture.
I think you showed this in one of your slides, but what are the present delta M1s, T squared, and delta M2, 3 squared?
So those numbers are known very well, and they're measured in electron volts squared. One is about 10 to the minus 3 electron volts squared, and the other one is about 10 to the minus 4 electron volts squared. And this, by the way, is another mini surprise in the neutrino sector, is that it looks like the masses are not very different, at least of the ones that have a non-zero mass. But these are the numbers. So it's 7 times 10 to the minus 5 and 3 times 10 to the minus 3 for the differences of the masses squared.
I have one question, which is, what's the next result, experimental result, that's most interesting that's on the horizon, and what's it going to tell us?
That's a very good question. I will give you my answer. What's happening right now is the T2K, from big neutrino oscillation experiments, there's a T2K and NOVA experiments going on. One is in Japan, the other one is in the US. And they are collecting more data, and they're giving us more information on CP violation. They're not going to give us much more information than the plot that I showed you. Those error bars will not shrink much more. I think the big thing that will happen with both the NOVA experiment and maybe with something like upgrades to IceCube, is that we'll get to learn what the ordering of the masses is. So I think the next result, which I think will happen before, say, the Dune experiment or Hyper-K turn on, is that we'll know what the ordering of the masses are.
So how long will that take us?
I would say, I'll make a guess, 3 to 5 years. And that will probably come from a combination of experiments. So NOVA will have some hint. You combine that with T2K, combined to, say, the Diabe experiment. All of that combined will say that one ordering for the masses is preferred over the other one. And because it's a binomial thing, it's either one or the other. Once you rule the other one out at pick your favorite sigma level, everybody will start believing that that's how the masses are ordered. That will probably happen before anything exciting happens in the rest of the story. That's my guess.
Can you flash back
the numbers? What I encourage you to do is to look at this great reference here. They are the ones who combine all the data, and they have a website which they keep updated. It's called a NewFit. It's a really nice website, so I encourage you to look at that. It has all these nice looking pictures as well.